Hello, calculus students. Today we're going to be taking a look at section 7.3. Along with that, though, you will be wrapping up the last three questions from section 7.2. So let's take a look. So section 7.3, and again, just as we've noted in the past, we've got an icon here at the top of the section notes of which you can print off prior to filling in to make things a little bit more advantageous for yourselves. All right, so let's take a look. Section 7.3, the volume using the shell method, or volume using the shell method. The shell method works this way, and it's an alternative method for finding the volume of a solid of revolution, and it's called the shell method because it uses cylindrical shells. A comparison of the advantages of the disk and shell methods is given later in this section. Consider a representative rectangle as shown in figure 7.27, where W is the width of the rectangle, H is the height of the rectangle, and P is the distance between the axis of revolution and the center of the rectangle. When this rectangle is revolved about the axis of revolution, it forms a cylindrical shell or tube of thickness, W. Look at the picture. Clearly, if we were to look at the rectangle in the picture where, again, you've denoted H as the height, W as the width, revolving it about the axis of revolution highlighted as such here gives you this kind of shell-looking object, this cylindrical shell. So to find the volume of this shell, we're going to consider two cylinders. The radius of the larger cylinder corresponds to the outer radius of the shell, and the radius of the smaller cylinder corresponds to the inner radius. So in two different instances, they'll highlight for the outer radius the following equation, or expression, I guess, P plus W over 2, and the inner radius, P minus W over 2. There's a bit of calculation that I don't want you guys to concern yourselves too much, if at all, with, but it does end up looking something like this. 2 pi times average radius times height times thickness. You can use this formula to find the volume of a solid of revolution. Okay, I'm going to scroll down just a bit more because there is a little bit more explanation that you don't need to concern yourselves with. But it does lend itself nicely to a whole variety of areas that are revolved around a certain axis of revolution and plane regions. For example, in this particular instance, you've got this triangular region, you've got this rectangular representative region, delta y, for example, and if you were to revolve it, you'd have the solid of revolution formed below. I would still consider this the shell approach, but in this case, you can see here how the object is a little bit more complicated than the prior example. And yes, an integral will take shape, as you'll see here. Now, on the next page, you can see officially the shell method takes shape, and for our purposes, the actual integrals that take shape. So here's how this is going to work. To find the volume of a solid of revolution with the shell method, you'll use one of the two formulas below. The horizontal axis of revolution, in other words, dy, or delta y, if you remember that, same deal, such that v equals 2 pi times the integral from e to d of p of y times h of y times dy. So you're multiplying three different aspects here. And then the same goes, except if it's a vertical axis of revolution, v equals 2 pi integral from a to b of p of x, h of x times dx. So if you consider the idea of, well, with the first picture here, delta y is a representation of a horizontal representative rectangle, which is parallel to the axis of revolution. A vertical delta x, or just representative rectangle in this case, if it is delta x, again, parallel to the axis of revolution, in this case a vertical axis, speaks to, again, the formula that we're learning here today. Let's take a look at example 1 and start applying this. Using the shell method to find volume. Find the volume of the solid of revolution formed by revolving the region bounded by y equals x minus x cubed and the x-axis such that x is between 0 and 1 about the y-axis. Okay, so we're going to start this whole problem off simply by highlighting our in this case, x minus x cubed. The h of x in the context of the problem is the function that they gave you to start with. And when we consider the revolving about the y-axis in this case, and the picture kind of nicely speaks to this, we're noting that our representative rectangle, which is a delta x representation, will be revolved around the axis which is parallel to that rectangle. Let me give you guys some more specific perspective here. And I'm going to jump to P of x to kind of help out in that analysis. So we can see that, I'm going to draw a little dashed line here. We can see that the P of x, in this case, simply just x. So quite literally the distance from the point here and the point here, and any rectangle for that matter, we can assess as just P of x equals x. But again, the representative rectangle is parallel to the axis of revolution, so that is in fact our P of x, which I'll write aside. Okay, so now we're actually ready to set up our volume equation. So volume equals 2 pi, because again, this is a shell that we're incorporating from A to B. We'll talk about the lower and upper bounds in a moment. And simply, again, according to the formula up above, it's P of x, H of x, P of x. But then we put it all together in the sense that we know A, the value here of which 0, 1, the ordered pair, giving us, though, the value of 0 for the A and B, 1. We could go ahead and use those as our lower and uppers, upper bound values, and then, of course, P of x times H of x, and then, of course, then D of x, or dx. We do the math here, a little bit of simplification. We'll end up with the following coordinate, of which this is not terribly difficult to then calculate the volume. Make one correction, I just caught it, where my ordered pair here technically is the origin. I apologize. There we go. Nonetheless, though, you are still just using the x values. Okay. If we continue this, we'll do a little bit of analysis. It's not terribly difficult, like I said, such that we'll have 2 pi times the integral of x squared, of course, is x to the third over 3. This x to the fifth over 5. And with some analysis, further analysis, which you guys know, simply plugging in 1 and then plugging in 0, we'll have the following quantities. We'll have 2 pi times, we'll have 1/3 minus 1/5. And then if you plug in 0, well, that's 0 for both. 0 over 3 minus 0 over 5. You simplify that one more step, distributing the 2 pi, you'll end up with 4 pi over 15. And that ends up being the volume of the solid of revolution formed by, again, revolving that shape or plane region simply about the axis. Revolution, which again was the vertical axis or y-axis. Let's move on. Example 2, using the shell method to find volume. So again, we're going to be doing the same basic thing, but we have obviously a little bit of a different look here. Find the volume of the solid of revolution formed by revolving the region bounded by the graph of x equals e to the negative y squared and the y-axis such that y is between 0 and 1 about the x-axis. So notice our function, and given our axis of revolution, delta y as opposed to delta x will be utilized. So let's highlight some of the basic components to start with. Instead of h of x, we're going to use h of y. If, again, you're wondering where this is coming from, consider the idea that because our representative rectangle is parallel to the horizontal axis of revolution, we're doing this with respect to y, so everything will be written in the sense where it's, well, instead of y as a function of x, x is a function of y. So here's your h of y equation. Nicely enough, though, it's written already for us, essentially. What I do is just write it down as you see it. And then as far as our p of x goes, technically p of y this time, right? We're looking at this. And if we were to take a look at any representative rectangle that's horizontal in nature, from that point to that point, which I'm going to label as 0, 0, it'll look something like that. Okay, so let's continue. As well, first we should also note what it was. P of y equals y, right? So as far as our integral, yet again, we're going to use v equals 2 pi because this is a shell. The integral from c to d. If they used e in the formula up above, I might go back and change that. So it should be c. Integral from c to d of p of y, h of y, dy. So let's start plugging some things in here. So we've got 2 pi times the integral from c to d. Now for our purposes on this problem, because we are talking about everything in terms of y, let's go ahead and find this point right here as 0, 1. So my lower and upper bounds should simply be 0 and 1. We make the connection to we did on the last problem in terms of x, but now this in terms of y, relating the two. So again, the integral now from 0 to 1. My p of y is just y. My h of y is e to the negative y squared, and of course still dy needs to be in the mix of the integrand. This problem does entail a little bit more analysis to integrate. I'm going to go ahead and use u substitution, particularly if I call u negative y squared. Let's reflect back. I know it's been a bit since we've done this, but you can assess the differential then as such, negative 2y dy. And that's going to help us then kind of frame what the integration looks like. Keep in mind, when we're relating to the following kind of generic integral, e to the u du, well, that's nice because that's just simply e to the u plus c. That's a indefinite integral analysis. We're doing a definite integral, so I'll bring into the mix the lower and upper bounds, but not until we've simplified it a bit more. In other words, I'm going to multiply inside by negative 2, because there's your du right there, negative 2y dy. And then, of course, outside the integral, I'm going to move my equal sign a little bit so that I can incorporate times negative a half. So you're kind of balancing, so to speak, inside and outside the integral such that it in fact does take shape as e to the u du. So outside the integral, we've got negative pi. This in its entirety does simplify quite nicely. It's just e to the u. I'll use what u is in fact negative y squared to be in the first place, or what we said it was. So go ahead and do that, and then of course from 0 to 1. Now we can wrap things up so that this equals negative pi times the quantity. If you plug in 1, that's 1 squared, but of course negative 1, because that negative is applied after the fact. So e to the negative first, which is 1 over e. Plug in 0, e to the 0, of course, is just 1, so that's minus 1. And that then ends up being, if you calculate this on your calculator, 1.986. I will wrap these notes up in a separate video, or have you guys wrap them up on your own looking at the past 7-3 notes via OneNote.